In this third example, we have the relative density of air was measured at various altitudes h. The results were, okay, so you have this one 0, and then you have 1, and if you increase with 1.5 kilometers, then the density of air becomes smaller, and as you go higher, then the density becomes lower. So basically this seems like a linear relationship, but let's see. Okay, so having encoded, okay, so you have, okay, so the first polynomial with 0.02, not bad, 0.001 for quadratic, 1.7 for third degree, and for fourth you have 1.86. so basically we choose between the first and the second because as you go higher, higher degree, so the value of standard deviation is higher, so we choose from the first and the second, and significantly second degree is better. Okay, so we start this one. So here you have the first, so these are the points of the equation, the x theta. Okay, so these are the 7 points of, sorry, that point. So actually there's a function called that poly, so I forgot to run this one here. Okay, so that poly, so this is a function that plots based on the lower and higher value of your x theta, and then also the yeah, just a plotting function. So going back, we have that same graph. Okay, so the points, oh, it's a very good representation. And for the second quadratic, you can see a well distributed, or a line that can really fit the points. Okay, and for the third degree, almost similar to quadratic, and for the fourth degree also, but yeah, so in this case we will choose the second, m is equal to 2, or the quadratic equation. So one rule when choosing the degree polynomial: choose the lower degree m, okay, without compromising the standard deviation. Meaning in this example we will choose the second degree because we have a lower standard deviation compared to the first. The second example previously, so we have very close first degree and second degree, so in this case we will choose the first degree polynomial, or the linear equation. Okay, that's it. So thank you so much for watching this video.